Okay, good afternoon everyone and welcome to this afternoon Kirk Lecture. So it's going to be given by Professor Barbara Fantechi, who's a Kirk Fellow here and who will be staying until June. And she's from SISSA and she's going to tell us about counting curves, which, how and why.
Thank you very much. So this is, there will not be terribly many mathematical details. It's more of a telling you of a story which is related to the fact that that in June we will have a workshop on enumerative geometry and equivariant methods in them. And so I wanted to tell you a story about the enumerative geometry so that you know a little bit what it is. It's a very classic, very classical topic. It means you want to count the solutions instead of finding them, or maybe as a preliminary to finding them. And there is one example which I think you are all familiar with, which is that if you have a polynomial of a certain degree, it has a polynomial of degree n, has n zeros counted. And here we have to be immediately careful. First of all, we have to count with multiplicities. And secondly, we have to take complex solutions, because this is a polynomial of degree 3, and if I put the horizontal line here, it has 3 zeros, but if I put it here, I can only see 1, but there are still 3. It's just that 2 of them are complex conjugate. So what we will be talking about today is complex enumerative geometry. There is real enumerative geometry, but typically the first step is study the complex one and then start worrying which results will, what will be true in the real case, how many of the solutions will be real. And as I told you here, I described the zeros of a polynomials as intersections of the graph with the horizontal axis. And we have a more general theorem by Bezout that says that if you have a curve C of degree D and a curve C prime of degree E, then they have D plus D times I points in common. And you can immediately see a problem here that even with lines, this isn't always the case. And of course you can say, well, take general lines, and this is something you do. But my favorite approach is to say that we actually work in projective geometry. Projective geometry means informally something that comes from the desire of painters to do perspective paintings, images in 2 dimensions that describe the world as we see it in 3 dimensions. So you must all be familiar with, imagine this is a train track which you are looking at from above, but if you were standing here, which might not be a good idea, but then what you would see is something like this. And there is something called the line at horizon, where of course my drawing isn't quite precise, but if it were done correctly, the 2 sides would meet exactly in 1 point at the horizon or line at infinity. And so the mathematical counterpart of this is that we take our problems, which will be in some Rn, we put this Rn inside the Cn, and then we complete it using points at infinity, and we work in projective space. And so what is the difference? The difference here is the hyperplane at infinity, and this is just Cn minus 0 divided by C star. So, or think of it as real, what you are adding is 1 point per direction that a line can have. The vector direction of a line, the vector direction is not unique, it's unique up to scalar, and it's non-zero. And so what you are doing is you, on a plane, you are adding essentially a circle that corresponds to all the directions, but be careful, you would think you get a disk, but you don't, because the direction straight ahead and the direction straight back are the same. Of course, over the complex number, this doesn't even make sense, but if you want to keep your real intuition, this is what we will be doing. So whenever I will speak, I will tend to make all my drawings and use my intuition here, but the actual theorems will take place here. Take the habit of. And there is one more thing I want to say, that the hard part in such theorems is actually to prove that there is a well-defined solution which does not depend on the input data. So how do you prove Bezout, for instance? Well, for the lines we know, and in general, well, I take one curve to be D lines. Each line is defined by a polynomial of degree 1. So if I multiply them, the union is given by the product. And the product has degree D. And then I take E lines in another direction. So basically, this will be a polynomial of the form x to the d plus a x to the d minus 1 plus lower order terms. And this will be similar. And here we can directly see that there are d times I points of intersection. So the hard part is not to compute the solution in many cases, but to show that a particular solution you can find gives you the general result. Okay, and today we will be talking about counting curves. So we can start with the easiest example. There is one line through two given points. There are some classical results, like if you give 4 lines in space, there are 2 lines which intersect all of them. If you want to try a similar trick, you want to have a funny exercise, you can do the case where 2 of the lines intersect, the other 2 intersect, and the 2 planes, thus defined, also intersect in a line which doesn't meet any of these 2. And you can check that you get the 2 lines. Exercise, find which ones. And any smooth cubic surface, so any degree 3 polynomial which defines a non-singular object, contains 27 lines. This is a very classical result. Italians are required to learn at least 3 proofs. And the next one is a result which is so famous that there is even a book with title 3264. And very recently, an explicit example has been constructed of real conics, such that all those 3264 are real. And it is a very non-trivial fact demonstrated by a group of very famous mathematicians, and the coefficients are rational numbers with like 6 digit or 7 in numerator and denominator. So it's the real stuff is tough. And when we count solution, we work with expected dimension, and expected dimension means what we expect from linear system. That you get a finite number of solutions if you put as many constraints as you have variables. And more generally, you have the expected dimension, which is how many parameters you start with minus how many equations. So now I want to start moving, we will be discussing something which has become known as Gromov-Witten invariants. But we start very informally saying that we want to count not just curves inside something, but maps from curves to something. So first of all, what is the something? And the something, I called it here projective variety, and you can ignore the details because there is a big theorem of Chow that says that as far as we are concerned, a smooth projective variety is just a complex manifold, compact manifold, which can be described as a closed submanifold, necessarily closed because it's compact, in complex projective space. Notice that typically real manifolds go in Euclidean space, but if you want everything to be complex and so the coordinates to be holomorphic, if your manifold is compact, each global holomorphic functions, like a coordinate, has to be constant. So you have to embed it into something else. Turns out the best place to embed it is projective space. So we are living at the intersection of two fields. Algebraic geometry, where the accent is we work with polynomials, everything has a degree, everything can be described by finitely many coefficients, and holomorphic geometry, which is we take our usual calculus favorite tricks and we just make sure that all the differentials are complex linears, that all the coordinates are complex, and that everything respects this complex structure. And beside the theorem of Chow, so that I will interchangeably speak of smooth projective variety or projective manifold, there is a theorem of Riemann. And Riemann tells you that if you start with a two-dimensional orientable surface and you put on it any holomorphic structure, so charts which are from C and the coordinate change is holomorphic, then automatically it is projective. This is a very non-trivial task, and in higher dimension, given a complex compact manifold, determining whether it's projective is an interesting question, but for curves, this is very standard. And so we have two invariants for a map. So we will always consider some smooth X in Pn, complex manifold, and we will consider maps, holomorphic maps, where this will be a Riemann surface. And so to this we can associate two numbers. One is the genus of the surface, and the other is the degree of the map. And the degree means that if inside this space I take a linear subspace of codimension 1 generically, how many points are in the inverse image? And if one wants to be technical, one can slightly generalize the degree as by taking something called the homology class. So if you know what it is, we work with it, but if you don't, it's a variation on the degree. And let me give you a basic example where the two methods, algebraic and complex analytic, overlap. If you take all lines in 3 space, you get something of dimension 4. Why? Because, for instance, you can parameterize by intersecting with 2 planes, or you can intersect with one plane and then give one direction. And the directions in 3 dimensions are 2-dimensional. We'll see that later. And then if we want to count, how many of these lie on a cubic, well, on each line, we will see this in a minute, but if you parameterize it, you get that each cubical polynomial induces a degree 3 polynomial on the parameter, which has 4 coefficients. So we get what is a rank 4 vector bundle, and if we choose a specific cubic, we get a section. And there is a general result that says that if your object, you have a smooth variety, smooth compact variety, smooth compact projective variety, and a holomorphic vector bundle, and you look at the zero locus of a section, this can be calculating by integrating the number of points you get if the rank and the dimension are the same, can be computed by doing some integral. So this is just, you have a top differential form and you integrate it on an orientable manifold. And so this is how you do it. And now we would like to do this in general. So what about now? This is how I count how many lines are in a cubic. Again, we will go back to this. And what about in general? If we fix the manifold, the genus, and the degree, and we look at all maps with that property. And this has what is called the natural structure of moduli space. So again, it has a geometric structure. You just take these as points, and like with a Grassmannian variety of lines, there is a natural way to put charts. And the conditions we can be interested in can locally, at least, be expressed as vanishing of a section of a vector bundle. So we are really like in the previous case. But then things immediately go wrong. So first of all, what we get is not compact. And this is something you are all familiar with, because, for instance, if you take x is equal P2, the degree is equal to, and genus 0, which means that the curve we start with is P1, so it's just a line. Well, now you're looking to maps of degree 1, of degree 2. And remember, this 2 means holomorphically, so you might recognize such a map. And from the viewpoint of complex projective geometry, this is how it looks like. And this has degree 2, and you know it, this gives you a circle. And similarly, you can produce an ellipse and a hyperbola. Sorry, I know I shouldn't use this. But when you go to the limit, let me go to the next board. If you consider a hyperbola, and this is also degree 2, and you can check that this is also rational, it's also the image of a line, because it has an explicit solution, which is this. But when A goes to 0, you get something which is no longer the image of a P1, and instead you get 2 lines. One goes to another. And this phenomenon that to compactify, so now remember we are in dimension 2, it means you start with something like this, which is how the projective line looks like, because if you have only one line, there is only one direction, so you have the projective plane and the point at infinity. And then it can degenerate, so to speak, to 2 lines. And here I am limited by my ability to draw, because this drawing represents 3 space, but this is actually a transverse intersection like here. Only to intersect transversely 2 things of dimension 1, you need dimension 2, and to intersect transversely 2 things of dimension 2, you need dimension 4, which I don't know how to draw. So I'll ask you to imagine this. And this phenomenon that you can, so we can add this structure. And by the way, I didn't tell you what kind of structure, but there is a workshop called moduli stacks. And the thing I'm hiding under a very thick carpet is what a stack is. As far as I'm concerned, I'll pretend it's a space. And it behaves very well. And the good news is that there is such a natural compactification. The first version comes from Gromov. It's a result in symplectic geometry. And he described this phenomenon. Notice that even if you start with something of higher genus, when you degenerate, you don't attach another one. You still get that you attach lines, you attach bubbles, you attach P1s or spheres. So you can get something like this. So this was described as bubbling. In algebraic geometry, the corresponding construction was performed by Kontsiewicz and Manin, but it is based on the classical construction by the Lind and Mumford of compactified moduli of curves, which on turn is based on the classical Italian structure theorem for morphisms of surfaces. So this is kind of the good news, is very classical. But the final bad news is the object we get does not have, in general, a well-defined dimension. And we will see at least some examples where it doesn't have the correct dimension, and then we'll extrapolate from there what this means. And this not having a dimension is very bad, because if we want to have integrals, we need maybe not a variety. You see, the advantage of a complex variety is it can have some minor singularities. Because we are over the complex numbers, they are at least in codimension 2, which means from the point of integrating, they don't count. And so we can still do integrals and get numbers. But if we don't have a dimension, we don't know what to do. So what can we save from this disaster? We can at least compute an expected dimension. If I had more time and I knew you were all familiar with either differential or algebraic geometry, I could compute for you the formula. But it's not difficult. It's just, again, classical. And in particular, notice that this formula becomes very special when these two conditions are satisfied. These are called Calabi-Yau threefold and became kind of popular at some point. And in fact, we'll go back to who they became popular with. And the point is there, every expected dimension is 0. It is kind of strange, but it means you get a lot of numbers, and these numbers have an interest. However, the problem is that in general, there is, how do you get expected dimension D is because you take a rank R bundle on something of dimension D plus R, and then you take a section. And your bundle locally just means you are giving R equations in D plus R variables. But these equations may not be independent. And let me give you a very simple example. If you are in R3 or C3, and you have coordinate x, y, z, and you put these two equations, these are two equations, so you would expect 3 variables, 2 equation, dimension 1, but you see this is not the case. This is z equals 0, union x equal y is equal to 0. And so this is a plane union, a line. This is the kind of bad behavior we are expecting. And now I told you who is interested in this, and the answer is the physicists are. Edward Witten in this story is a theoretical physicist, and as far as I know, the only theoretical physicist to ever win the Fields Medal. So he said, well, we know that these things is pretty bad, but what if it weren't? What if it behaved exactly like we want it to behave? It's smooth, it has dimension d, and then there are a number of natural maps relating these spaces, and we want that they all behave very nicely. And then he said, well, if this is the case, then I can do lots of calculations. And came up with interesting relations between these numbers, and did something physicists tend to do when you have an infinite bunch of numbers. You put them into a partition factor, and you prove properties of them, and in some cases you can compute stuff. The original version of the first result you obtained was a method to compute the case where x is 1 point. So that you just look at the curves themselves. This is already very interesting, and it turned out that the formulas he conjectured are true, and the first proof was due to Kontsevich. So this takes place around the early 90s, 1991. Or this is, as I like to say, the point in which theoretical physics came and parked on my lawn. Because I didn't really have an interest in this, but it turns out I had an interest in a lot of the mathematics required. And so, how do you do when physicists show you a calculation and tell you, see, if you could make this rigorous, this would be nice. And so you try. So the first thing which was done is produce an axiomatization. So you make a formal statement of, I want to define invariants such that long list of properties. And then showed that if you could define invariants such that the properties were satisfied, then Kontsevich resolved this problem of counting plane curves of genus 0 and any degree. So genus 0 again means it can be parameterized rationally. It means it can be completely solved. So let me give you an example of something that can be solved. As I said, we already know that a line can be solved because it can be written with one parameter, and a circle can be solved because we have an explicit rational parametrization. And some cubics can also be solved. For instance, if you take this cubic and you try intersecting it with a line y is equal to tx, it turns out that apart from the origin, there is always one solution which you can compute because you get t squared, x squared is x cubed plus x squared, and this becomes x plus 1 is t squared. So x is t squared minus 1, and y is t cubed minus t. So this is what we call a rational cubic. And if you see it singular, it has a bad point where it intersects itself. Turns out that this is precisely the condition we want. That the cubics which do not have such bad points are not rational. And the condition to get something of finite dimension is something like through 2 points you get 1 degree 1 curve. Through 5 points you get 1 conic, degree 2. And through 8 points you get 12 such rational cubics. And in general, you count dimensions, you estimate the problem, and you get that for 3D minus 1 points, you expect ND rational, in this sense, degree d curves. And the ones on the blackboard were basically all that were known when this calculation started. In fact, there was a calculation for d equal 4, but that was all. And using physics method, Kontsevich calculated them all recursively, starting with through 2 points, there is a line. So, and this kind of problem had been open since the middle of the 19th century. So for us algebraic geometers were doing this for a long time, it was actually kind of amazing. So how do we make this rigorous? And of course, as usual, I felt that my methods didn't work. And in fact, symplectic geometry, here I'm cutting a lot of corners, solved this problem. And the way you solve this problem is you try to make all parameters as general as possible, and you hope this helps. And this is related to what I told you, that if you take a polynomial, of course, maybe it doesn't have as many roots as it has degree, but forget about the complex numbers for a moment. Most random polynomials do not have multiple roots. The multiple roots is a zero-dimensional condition. It's codimension 1. And so here what they did is they found different ways to perturb the equations in such a way that the result behaved really well. Was non-singular, was a manifold, technically an orbifold, but we won't discuss that, of the expected dimension. However, as much as they pressed, so by 95, like, they had reduced the problem enormously. A lot of cases were known, but not all. And at some points, in fact, algebraic geometry entered the picture. And so I was told when you give a talk, you should have at least 5 minutes that everybody, when they get out, will remember. So if you slept until now, wake up, because this is the 5 minutes. So this is about what is algebraic geometry, what are our methods, and how they can be useful to treating this problem. And so what I'm going to look at is a case of counting curves where the solution is, so to speak, obvious, and show you that when you look at it with algebraic geometry eyes, the solution is not obvious at all. And it has an interesting structure, which you didn't see. So let me start with the curve in the plane given by y plus x cubed is equal to 0. So it's done more or less like this. And now what I take is I take x in 3 space given by y plus x cubed is equal to 0. So what do I get? I get a family of vertical lines going through this curve. I put this curve down on the plane, and over each point I draw a vertical line. And now I ask myself, with what structure does the space of line contained in this x have? And you say, well, it's obvious, it's this curve. For each point in the curve, there is one line. And this is not how, this is the set, but algebraic geometry, as the name says, works with algebra. And so what we do is we look at these lines, and since they are vertical, in particular, I can describe every such a line by giving 2 parameters. I can write them if I have such a line. it has P0, and it has a direction vector. And this direction vector will have a non-trivial vertical component, which I will call like this. And this point I will call AB, 0. And so parametrically, my line is given by P0 plus TV. Or I can do the calculation and I get A plus TU, B plus TV, and V. And now what does it mean that it is contained in the locus y plus x cubed is equal to 0? It means that if I replace x, y, and z by A plus TU, B plus TV, and T, I get 0. I get the 0 polynomial. And so I write this polynomial. Of course, the z doesn't play a role. And what I want is not just that this has value 0, but this is the polynomial 0. I get 4 coefficients, and I calculated them, not for you, because I'm sure you can do it, but because every time I try to do it on the blackboard, I got rather random results. So you can solve the first 2 equations. It's b is equal to minus a cubed and v is equal minus 3a squared u. And you are left with these 2 conditions. And normally you would say, well, if u cubed is 0, then u is 0. And what algebraic geometry is good at is working with these things which have a power which is 0 but are not 0. They are nilpotent. And it's something actually you all were familiar with where you took calculus 1, because you all worked with things with up to t squared, up to t cubed, up to t to the 4th. And so for me, saying that u cubed is 0 means that when I develop things in power series, everything where there's a u cube or higher, I ignored, and everything where there is a 3au squared, where there is, let's forget about the 3au squared is 0, I ignore, but they remain non-zero. So what is, I told you this is called geometry. What is the geometry? That if you are in a plane with coordinates u and a, well, what you have, the condition u cubed is equal to 0, means that, okay, as usual, you have kind of a little thickness in this direction. It's infinitesimal, okay? Say you are ignoring millimeters, 10 to the minus 6, it means you can have something long 10 to the minus 2, because to the 3rd it will be 0. And the fact that you have au squared is equal to 0 means that actually, away from the origin, what you get is something smaller. So what you get is a double line and a triple point sticking out at the origin. And this is the kind of geometry that algebraic geometers work with. And if this example is actually not a new example, this is completely covered by the standard theory due to Fulton and McPherson in the 1980s, and actually earlier, before 1980, because 1980 were the first nodes. And what you get is, now I took this specific example. I told you that a cubic has 27 lines. And so what happens is that if you take a nice cubic one without, which is not rational, without singularities. If you take C, non-singular cubic in P2C, and you do X in P3C, P2 over the complex number, and you take X given by the same equation, just as I did, what you get as a space of lines is a copy of your cubic with multiplicity 2, and then at each flex, notice that here the point, the origin is a flex of the original curve, and it turns out that at each flex you get an extra little something. And it turns out that the cubic contributes 9, the double cubic contributes 18, and each flex, of which there are 9, contributes 1. And so you get an 18 contribution from the double curve and a 9 contribution from the flexes, and this is another way to recover your original 27. So this is the kind of calculations algebraic geometry can do. We start with something which is completely elementary and completely smooth, and we get non-trivial algebra going on, and we can use this algebra to do calculations. And the advantage is that we already have a structure equipped to work with singularities. So the algebraic geometers first recast the problem in terms of cycle classes. If you don't know what this is, it just means objects on which you can take integrals of differential forms. So this is, it's something called the Borel-Moore homology, if you like. But the point is, this is something which is well understood and well known. And in fact, then in 96, Li and Tian constructed such a set of classes, showed that there was a general principle that worked. And in fact, there is a big gap between when, there's about 2 years between when this result was announced and when it was actually published, partially because it always takes forever to referee, but also because it's a technically which is very demanding. What they do is they construct local pictures and glue them, and this requires some skills. And as usual, you know, there is this idea like my grandfather could make a chair from scratch, and it's a lot of work and you get a very beautiful chair. But nowadays, I don't know about you, but I tend to go to IKEA and I get a flat pack, and then I give the flat pack to somebody who knows how to do it, but I can even do it myself, and we get an ugly chair, but it's very fast. And so this is how I entered this story, because of course if I tell you this is because I have been involved in it. What happened is I went in 95 to a conference and I heard Jun Lee describe what they had done. And I knew already Kai Behrendt, who had worked on this with Yuri Manin, and I went to him with my notes and said, well, look, here these people are constructing cones in obstruction spaces of deformation functors. There must be an easier way to describe them. This must be something which we can recognize and which exists naturally and thus glues, because it is itself, so to speak. So we don't have to glue anything. Well, this is maybe my one-sided recollection. I'm pretty sure Kai will tell you something completely different. But what is true is that we did, putting together our respective knowledges, which means 3/4 chi and 1/4 I, produce a way to construct abstractly such classes, such virtual classes, in a large number of situations. And the point is, the proof is actually much easier. And the proof is much easier because it uses much, much heavier technology. It uses the hard version of algebraic stacks. It uses the PhD thesis of Illuzy, and it uses a rather obscure result of the linear, of which we make a slight generalization. And what made the paper useful was not the proof, but rather the criteria. So what we did is we provided a machine, not only a machine, but the controls for these machines, the instruction for building the chair, which were expressed in this language of infinitesimal deformation theory, which was, again, a well-established and well-known language. And so this led to a number of calculations. It led to connections both with theoretical physics and with integrable systems. In the meantime, also the symplectic geometers have found many approaches that work, and the two fields keep pushing each other and helping each other. For instance, one thing I would like to mention, since we are here in England, is that the original motivation for Li and Tian was to work with an algebraic definition of something very analytic, the Donaldson invariants. And this became possible, but not in full generality. And keep that in mind, because we will be going back to there. So there is a technical problem, which means that at some point, instead of saying, okay, for each isomorphism classes of object, I put a point, semi-stability means that some of the points get scrunched together. And this, as you can imagine, is not good. And, well, what happened? This was, I think, the first point where people started to pay attention, because when Richard Thomas extended Donaldson results to dimension 3, he did not use analytic methods, he used algebraic methods. And this was stunning because, of course, if you have Donaldson there, it means you have all the analysis you need. But the point is the algebraic methods were really easier to use. And again, became extremely popular also with physicists. And there is still ongoing work of variation on this. So what does this all have to do with equivariant methods? Remember, this trimester is called Equivariant Methods in Algebraic and Differential Geometry. Where did I hide the equivariant? And the answer is, well, there is something is hidden at the very beginning. I told you we are making these moduli stacks, but I didn't tell you how. And typically what you do is you put extra structure, what is called the framing by a group. You get something very nice, and then you have to quotient away by this group, doing some variation of geometric invariant theory. So this is, for me, one of the oldest connections between linear groups and algebraic geometry. This is something which, there is a beautiful book called Geometric Invariant Theory, and it has 3 editions which become larger and larger, and it's still valid. It starts from the 70s, and it's still a key technique. Then there is torus localization. So when you have a linear group acting inside the group, there will be always a maximal torus. And there is a formula. I told you at the beginning we were integrating cohomology classes on a manifold, and there is a so-called localization formula when the whole construction is equivariant with respect to a torus. And basically, like immediately after the virtual classes were defined, the localization formula was also extended. And this became a very important tool for both computational and theoretical reasons. Because computational is clear because this is a computation technique, but it's also theoretical because I told you at the beginning everything was supposed to be compact, everything was supposed to be projective, but once you can do localization, all that counts is the fixed locus of the torus section is compact. And so this enlarged enormously the amount of calculations that could be done. And finally, I told you that there was a problem with the semi-stability. And I think around 2017, Francis Kirwan found a canonical, beautiful way called Kirwan blowups to, say, okay, you are an ugly space, you have this semi-stable scrunching, and I do something to you which is super canonical, and you don't have problems anymore. You are a nice orbifold, and I like you. And a few years after that, there is a number, I chose these two names because this is the paper I know, but a number of people have worked on it. They said, okay, we have the classic version and we make a virtual version. And now we have also this tool, which means we are no longer limited by the problem of what if there is a semi-stable scrunching going on. So you can see that it's not just a collaboration at the end of the story, but it's a collaboration all the way. And yeah, here I would have many more slides listing what else has happened ever since, but I think I'll close here. Thank you so much.
Thank you, Barbara. Other questions? Well, maybe I can start by asking one. At the beginning of your talk, you mentioned that in some ways it's nice to find a nice example where you can actually solve the problem. But then you didn't explain how that what this one nice example can lead you to solve the problem in general. So, for example, for counting problems, you first look at
So the point is, you have to find a way. You typically have that your problem depends on parameters. Like if you have, in the case of Bezout, you have two curves. So each of them is given by a polynomial. And if you have a polynomial of degree d, it means it's a combination of monomials. So you have so and so many parameters, which are the coefficients. And what you want to prove is that there are two approaches. One approach, which is the one of Fulton-McPherson, which says for any value of the parameter, I can get a number, and this number doesn't change with the parameter. This is or you can do it, okay, maybe not really for all of them, but for most, like with polynomials of degree 2, they have two roots until the discriminant, unless the discriminant vanishes, which is given by one equation. Now, one equation over the real disconnects because it's codimension 1. So on one side of discriminant 0, there are the polynomials with two roots, and on the other side, there are polynomials with 0 roots. But when you are over the complex number, one equation has codimension 2. And if you take away something of codimension 2, like a curve from 3 space, it doesn't disconnect anything. And so this means that the number of solutions does not vary as you change your parameters. And this is a very, very old idea. It's called the principle of conservation of number. And the trick is to show that the advantage of the Fulton-McPherson is that instead of saying, well, if everything is generic, because the case I told you of the lines meeting is certainly not very generic, but if you can do it for any line, then at any point you compute, the number will be the correct one. So the key trick is to show that there is a number for any value of the parameter and that this number is conserved.
So do you have any idea how to construct virtual cycle when there is a three-term perfect obstruction theory?
I think this is probably one of the most asked questions. And in fact, I wish I had a general answer. I think there would be an enormous interest. So there, let me mention two different sides to this. So in one sense, sometimes when there is a third piece you have to keep track of, there are ways to get rid of it. So there's something called, for instance, co-section localization, which is a technology which does exactly that. On the other hand, I think there are counterexamples that if you want to go in really full generality, you cannot do it. And you cannot do it for very simple reasons. So you see, the way you get something of dimension more is that, how do? You have the number of parameters minus the number of equations. But then you can say maybe these equations aren't really very independent. Maybe there are relations among them. And so what you expect is that the actual number of equations doesn't count, but you have to count this, the number of equations minus the number of relations among them, because you don't really expect that the dimension go down as much. But now you see I can do some math here. And what can happen is that the expected dimension you get is actually larger than the space you are in. And this tells you that the result is there because there is only one class in that dimension, which is 0. And this can be fine in a number of cases, but it can also be less than illuminating. And so I think there is room for working in this direction, in particular with the other key technology, which I have not mentioned at all, which is using derived geometry. So in derived geometry, these structures with expected dimension are really viewed as smooth higher structure, but they are smooth with higher kind of limited, with a very small length, 0 and 1 parameters and equation. And there are a number of problems, extremely natural, where you get exactly this. And we have the structure, and we are trying to figure out what to do with it. So there is still hope, but maybe not in general. We will need more structure, and we expect this structure to come from derived language.
Are there any more questions for Barbara? Okay, then I think we thank you again.